Welcome to this talk on 3D mathematics, rendering the hardware and the PlayStation 2. The first part is going to be about essentially linear algebra and how it applies to 3D graphics. Then we'll go a bit about over the rendering pipeline, like the different steps, how to get pixels on the screen in a 3D way, and about the historic evolution of 3D hardware from like the starting in the 60s, and then specifically we'll talk about the PlayStation 2. Okay, so let's start with arrows. There are two things that we want to do with that we can do with arrows, and one thing is if we have two arrows, we can put one arrow at the end of the other arrow and like connect the beginning to the end like this, and we call that addition of arrows. And there's another thing we can do, which is scaling, and that's essentially just changing the length. So 1.5 times this arrow will be this arrow, but 1.5 times as long as the original one. And we call that, well, either scaling or multiplication or something like that. And we can do both at the same time. So we can take this arrow multiplied by minus 0.4, for instance, which scales it down and flips the direction. So multiplying by negative values flips the direction. And we take this arrow multiplied by 2, and then we add the result. So this is our small scaled arrow, and then add this one to it, and we connect it, and we get a third arrow. And we call this a linear combination. So a linear combination is any combination of addition and scaling of a bunch of arrows. And this like defines what we can do with arrows. So now it gets a bit math heavy, like abstract into the definitions and so on. We can convince ourselves that any arrow that we can how do you explain this? Like all linear combinations of a set of arrows that we're starting with taken together, we say that spans a whole space. So all the possible arrows that we can express like that by just picking all sorts of numbers for the scaling factors and adding them all up in whatever ways, all that thing gives us a space of arrows, and we call the original set of arrows that we started with the spanning set, and the span of that spanning set is that space. So as an example, we can take these three arrows here in the braces, and the span of that will be the whole plane of the screen, essentially, and every arrow that we can draw on the screen is part of that span. Like for every arrow, we will find some linear combination of these three arrows that will be that arrow that we want to express. But we notice also that we have actually more arrows than we needed in this set. So these are three arrows, but actually we can express any of the three arrows as a linear combination of the other two. So yeah, we have in this set a bit more than needed. So our spanning set is not quite optimal, you might say. And this brings us to a very important notion of a basis, which is a minimal spanning set. So we take only the number of arrows that we need to span the space, and we call that a basis. And the basis is like we can choose any basis that we like. It's not like we don't have to. We have a huge choice of bases, is what I want to say. But often we will choose an orthonormal basis. So like on the right here, which means the arrows will be perpendicular, or orthogonal, which is the ortho part, and they will be normalized to a length of 1, and we'll talk about length a little bit later, which refers to the normal part. So that is a very common basis to use. But it's we can really choose any basis. And the interesting thing is that any basis for a given set will have the same number of elements, and we call that number of elements the dimension of the space. So, for instance, with these three arrows, which span really the same space as just two of these arrows, we'll have a two-dimensional space, and that makes intuitive sense because it's the space of the screen, and the screen is two-dimensional, of course. But if you imagine one of these arrows like sticking out of the screen, you will have a three-dimensional space. So that's kind of these are some very important notions. And now we want to write our arrows in vector notation. So any combination of these three arrows, say, let's say one of these arrows is sticking out of the screen, so the three arrows make up a basis. So we say we multiply one of them by A, one by B, one by C, and we just stack these numbers on top of each other, A, B, C, as a column, and that is the vector notation that we use. So our basis vector v1 will be 1, 0, 0, v2 will be 0, 1, 0, and v3 will be 0, 0, 1. And now the two operations that we can do with arrows, we can see that we can express them in this vector notation, and we see that if we scale an arrow or a vector by a number, what we do is just scale each individual element multiply each individual element by that, like the number. And to add two arrows, we add corresponding rows. So A plus D, B plus E, and so on. And this is really a general idea. It's not really about just arrows. It started with arrows historically, but you can think of the base as really anything that you want to count at the same time. So let's say apples, bananas, and cherries. You might say A stands for how many apples you have, B stands for how many bananas you have, and C stands for how many cherries you have. And then saying like my neighbor has 2 times as much fruit as I have, it means he has 2 times as many apples, 2 times as many bananas, and 2 times as many cherries. And if I want to say, okay, the fruit of my neighbor and mine, we kind of bring that together, which means we add them. It means, well, the apples that we have together will be my apples plus his apples, so it's A plus D, and same with bananas and cherries. So we add the individual parts. And a vector space is really just about counting different things at the same time. It's really a very, very simple notion, but it happens to work very well with like arrows and things that we do geometrically. Okay, let's not get to the slide yet. Let's stick with the fruit. So let's say I have 2 apples and 3 oranges or something like that, and I go to the market and I want to exchange it for something else. Theoretically, I could like bring my 2 apples and I might get a banana for it, and I bring 3 oranges and I get a pineapple for it. But if I bring 2 apples and 3 oranges at the same time, I may get something else, like a melon or something. And that's kind of weird. I mean, it's not really completely unreasonable, but you'd think that, like, if you bring your fruit separately to the market, it should be the same as bringing everything to the market at the same time. Like, if I bring 1 apple and another apple, it should be the same bringing 2 apples. And that concept, like if you think about it mathematically and express it in a mathematical way, that leads us to the idea of a linear map. That means, so think of F as the market we're going to, and A, the amount of apples, and V like being 1 apple, and B, the amount of bananas, and U being 1 banana. It means if I bring my whole collection of fruit to the market, it should be the same as, like, bringing A apples should be the same as bringing 1 apple A times and bringing 1 banana B times. And also I should be able to bring apples and bananas separately. So that means this this linear structure that we started with, the addition and scaling, that should be sort of transparent to the class of functions or maps that we're thinking about. So the map really only cares about the vectors in the abstract sense. And that's a very natural class of functions to think about. And this is what linear algebra is all about these linear maps and vector spaces. So we already saw that any vector can be expressed as a linear combination of a few basis vectors that we're starting out with. And we saw that the linear map only really cares about these basis vectors here. Like if v and u are my basis vectors, I only really have to know what v and u map to in that linear map, and everything else is determined by linearity. So let's just say f of v is v prime and f of u is u prime. And if I know these two things, I already have everything I know about f, everything that I need to know about f. It's completely specified by these two relations. And just as an example, here's something that is not linear. So let's say f of x gives me x, like maps to x squared. If I have f of 2 plus 2, that's f4, obviously. 4 squared is 16. But if I have f of 2, that is 2 squared, which is 4, and 4 plus 4 is 8, so it's not the same thing. So that is not linear. Okay, some examples. So let's say we're working with an orthonormal basis now. So one arrow is pointing right and one is pointing up. And one thing we may want to do is flip it horizontally. So we take the right pointing arrow and we make it left pointing. And the up pointing arrow will just stay the way it is. Another thing we may want to do is scale, let's say in the vertical direction in y. So we leave the right pointing arrow the way it is, and the up pointing arrow, we just scale it by twice as long. Rotation by 30 degrees, we take the right pointing arrow and rotate it 30 degrees, and we take the up pointing arrow and also rotate it 30 degrees. That's pretty simple. And that really defines the complete map. And now we go to matrix notation. So because it turns out that these linear maps are so simple, they're also really like economical to write down as just numbers, and we call that a matrix. So remember, we have our basis vectors v and u, and they map to some other vectors. And I'm just doing like everything in 2 dimensions right now for simplicity, but it's not really dimension dependent. And we see that like f of v, and v is by definition 1, 0, maps to some vector, and we'll just call it v prime 1 and 2. And same with u, our second basis vector will map to u prime 1 and 2. And to write that as a matrix, we just write it from left to right. Like first basis vector maps to this, second basis vector maps to this. And if we have more vectors, we just write them to the right of this. And the identity transformation, which does nothing, which leaves everything intact as it is obviously 1, 0 and 0, 1. You can see that from just, yeah, if that's like 1, 0 stays 1, 0 and 0, 1 stays 0, 1, you write them next to each other, it's that. Okay, so that's a matrix. Now we want to write this application of a linear map to a vector using a multiplication of that matrix with a vector. So we're just defining what it means to multiply a matrix with a vector, and we define it to mean just applying that linear map to a vector. And we can derive what that product looks like. So that is our general matrix, and that is our general vector. And we can just see that applying that vector in the VU basis is just x times v prime plus y times u prime because of linearity. So v prime and u prime are defined here. So v prime is that, u prime is that. We just plugged in v prime and u prime here. And now if we multiply, like pull x and y into the vector and add them, we get this expression. And this we'll just call x prime and y prime. And so we just derived what matrix vector multiplication looks like in 2 dimensions. So it's pretty simple, actually. Okay, now let's look at the linear maps again in matrix notation this time. So our mirror, the right pointing arrow is flipped, like it's multiplied by -1, so it points in the other direction. So we just write this as -1, 0. Scaling only the second basis vector by 2 means we just have a 2 in the bottom right here. And rotation by 30 degrees. Okay, now we have to know a little bit of trigonometry. The x part, like the right pointing part of this, will be the cosine, and the up pointing part will be the sine. So that is cosine and sine of our angle, 30 degrees. And the up pointing arrow, also quite easy. So we're gonna have the same numbers. X will be minus sine now, and y will be cosine. So minus sine and cosine, that will be our matrix. And like in a lot of material that you find online or in books, you kind of get this, like it looks like this rotation matrix falls from the sky or something, but it's really very easy to derive by just observing what the 2 basis vectors like will transform into under a rotation, and then just writing that down. Okay, so there's a question: what's the difference between a linear map and a function? Nothing really. Map and function mean the same thing. Okay, so we have some intuition about matrices now. But now it's really interesting. So F is a linear map and G is a linear map. If that is the case, then it turns out the composition of the two is also a linear map. So that means, what's a composition? That means G after F it's what you can say it like. You apply F to some vector, and you get a resulting vector. And you apply G to that vector. So you just send a vector through 2 functions after the other. And if we write the whole thing as a function, we can say, okay, G after F is like this function, which is the same as sending V first through one function and then through the other. And as we'll see that G after F will be linear down here. That means there has to be a matrix G times F such that it will be the same multiplying that matrix with V as first multiplying V with F, giving me some vector, and then multiplying that vector with G. So it has to exist, this matrix. We just have to figure out, like, find what the matrix looks like. And, well, that's actually pretty easy. So just applying F to some general vector, like V and U will be our basis again. And we know F is linear, so F really only cares about the vectors, and like the basis vectors. So this is the first step, and we call F of V and F of U just V prime and U prime. And we can, from this expression, we can read of the matrix for F. So it will be F and V prime and U prime as the columns. Okay, so we take this vector and now send it through G. And G is also linear, so it only cares about these vectors again. So we can write it like this: G of V prime and G of U prime. and we'll call these v double prime and u double prime. And from that, again, we can read off the matrix for GF. Remember, our input here was F multiplied by vector, so it already went through F. So this expression is what happens to the vector if we send it through F first and then through G. And we just read it off. Really, it's just G times V prime and G times U prime are the columns of that product of matrices. And it's really quite simple. I mean, you just take F and think of it as like a bunch of column vectors, and you multiply each column separately by G, and that's how you build your matrix GF. That's it. That is matrix multiplication, just derived quite like from very simple principles. It's just linear maps and vectors. And if you want to write the thing out like in components, like with 4 components for each matrix, well, you're gonna get this mess here with what is it, 8 products and 4 additions. It's not really pretty to look at. That's what you get for like from multiplying everything out. But the concept behind it is quite simple, I think. So we really only say that we want this multiplication of these 3 things to be associative, and that leads us directly to matrix multiplication. And this is a very cool thing, because any 2 linear maps, like if I have a rotation and a scaling and another rotation and maybe another scaling and another rotation, I can always multiply that together into just a single matrix. Okay. Any questions so far? I mean, if you have, then just write in the chat. Next thing we'll look at is the scalar product, which kind of connects length and angle of arrows, which is a very important concept. So in general, the scalar product, or the dot product, is calculated by multiplying each set of like corresponding coefficients and adding up the whole thing, like v1 times u1 plus v2 times u2 plus v3 times u3 and so on. But what is that geometrically? It's not very obvious just from looking at this formula, but it's not so hard to figure it out. The first thing that we check is what happens if we multiply a vector with itself. So we get v1 squared plus v2 squared plus v3 squared and so on. And well, it turns out that this is just the length of the vector squared by applying Pythagoras' theorem. So it actually works in any dimension. This is just a 2-dimensional case. v1 squared plus v2 squared is v length of v squared. I'm missing the length here actually. Okay, so multiplying or dotting a vector with itself gives us the length squared. That's very nice. And now we do a fun little thing. We just take any 2 vectors and add them, and we call one of them A, one of them B, and the sum of them C. Now, because they're the same, we can just dot every side with itself. So C dot C should be A plus B dot A plus B. And turns out we can multiply this out. You can convince yourself that this is the case. So this is the same as A dot A plus B dot B plus 2 times A dot B. But we already know that dotting a vector with itself gives us the length squared. So that is C squared plus A squared plus B squared plus A dot B. But we know that if A and B are orthogonal, then Pythagoras' theorem should hold. So we have C equals C squared equals A squared plus B squared if and only if A and B are orthogonal. And that means A dot B must be 0 if and only if A and B are orthogonal. And that's a very important result. Like the dot product between 2 orthogonal vectors is 0. This is extremely important. And it's very easy to show this way. And we also derive the law of cosines if you're into that kind of stuff. Okay, now we can get back to general dot products. So back to v and u. The interesting thing is we can now decompose u into a part that is parallel to v and one that is orthogonal to v. We call those u parallel and u perpendicular. Did I say parallel? Orthogonal, perpendicular. And we can multiply this out. So v dot this thing will be v dot u perpendicular plus v dot u parallel. But the fun thing is that v dot u perpendicular is 0, of course. So that thing just disappears, and we're left with v dot u parallel. And we didn't really show this, but it's not so hard to see that actually if you have two parallel vectors, the dot product is just the product of their lengths. And now we just express u parallel in terms of u and the angle between the vectors. And if you know a little bit of trigonometry, you will see that this is the length of u times the cosine between the vectors. And that's like the classic formula for the dot product that you will find everywhere. And I think this is a very simple sort of derivation of it. And it's important because it, you have the length of v, you have the length of u, you have the angle between them, so that thing pops up in all sorts of places. Okay. So now we're going to projective geometry. Until now, we only really talked about arrows and what we can do with them, their transformations. But we also want points. And one thing that points have that arrows don't is a position. I mean, that's kind of what they are. They are a position, essentially. So what we want to be able to do with points is move them to another place. So like add some kind of translation to them. So p prime equals p plus t is some kind of thing that we would like to express. But we can't do that with a matrix, really. We can't just add something with a matrix. Unless we can. Okay, so we go one dimension up. We add two-dimensional vectors. And this will actually allow us to express some additional stuff. So let's take the first case. We just add a 0 in the last dimension. And if we take any like a matrix of that shape where M is like sort of 2D 2 by 2 matrix that we've looked at already, and the rest is new. The third row and column is new, and we multiply that with such a vector. Then it turns out, like, because this is 0, the whole right column is sort of unused, and we just end up with x prime, y prime, and 0. So it just transforms the arrow kind of as before, and it stays an arrow because it's still a 0, and the translation part is it's not used. Okay, now the other case, we just put a 1 in the last slot, and actually we can multiply this whole thing by some scaling factor or a weight, but we'll just think of w as being 1 for now. So we multiply this matrix again by this new vector, which has a 1 in the last slot, and lo and behold, this causes tx and ty to be added to the x and y components, and the 1 to be put into the last slot here. So what we get out of it is again a point, and the components also have this translation applied to them. So this is very nice. So with the same 3 by 3 transformation, we can transform arrows and points like in a consistent way, such that they retain their character, so to speak. Okay, and here are here just a little bit of algebra, what we can do with this projective approach, also called the homogeneous approach. Yes, that was a question. So we also call this homogeneous coordinates. Yes. Okay, so let's take a point with coordinates p, and so we put a 1 because it's a point, and we add an arrow to it, and what we get out is the point, but with the coordinates changed by that, like moved by that arrow. So that's kind of exactly what we expect. If we subtract 2 points, well, we get an arrow from one point to the other point. Very nice. What if we add 2 points? Well, we now get a 2 downstairs here, but we can factor that out. So that means because we want to normalize it, which means we have a 1 downstairs. That means we have to divide the coordinates here by 2, and well, we have a weight of 2 now, but the point is actually midway between P and Q, so that makes perfect sense. Like what would you expect the sum of 2 points to be? It should be the point right in the middle, and that's exactly what it is. And if we add 2 points with different weights, it actually turns out by adjusting these 2 weights, we get any point that lies on the line through P and Q. So that's all very nice. And so this projective approach is really useful for expressing the difference between points and arrows. And also because it lets us express translation, but there's another thing that it lets us do, and it's perspective projection. So to project a point onto the sort of the retina or the screen or whatever, we have to calculate, like our point is P, we have to calculate this point P prime on the, let's say this is our retina of the eye. And we have another point back here. And notice they have the same y coordinate, but once they're projected, the point further away is, well, you might say it gets smaller. Like if you have an object that's further away, the object would get smaller, so it gets pulled to like the center of the view or something like that, which is what perspective is, of course. And to calculate P prime, well, it's actually pretty easy. So these are similar triangles at P prime and at P. So we have that y prime over z is y over z. So just divide this by this and this by this, and now we can solve for y prime. So it's just y times z prime over z, and for simplicity, we just say, okay, z is equal to 1. It could be anything, but it's some number we know. It's just something we plug in. So so if we say, well, actually it's z prime here. So z prime is 1. So for y prime, we just get y over z. Okay, that's easy. But we cannot divide with a matrix. So that might appear to be a problem. But it's not, because of projective coordinates again. So if we have this kind of matrix here, well, if we multiply it with any point vector, well, we get x and y here, and some weird thing for z that we don't really have to worry about. Just want to be general. But the interesting thing is, if we put a 1 here in the z column instead of the w column, then this last number here will be will like copy the z coordinate downstairs here instead of having a 1. And now to normalize this point, we have to divide the coordinates by z, and that is exactly the perspective projection that we need. So yeah, there we go. Projective coordinates give us perspective. Now we just have to make sure that the coordinates are sort of in range from -1 to 1. But that's just a scaling, so we don't really have to worry about it so much here. Okay, so just to summarize the linear algebra part, we started by thinking about arrows, and we came up with this idea of vectors, and it turned out that we can also use vectors to represent points. So we have 2 things in this scheme that we can do with vectors, and it's arrows and points. The scalar product is quite useful because it has something to say about length and Well, you might say similarity in general, like the angle between two arrows. It's also used as a similarity measure in AI, for instance, where words or concepts or whatever might be represented as vectors. Um, and a matrix represents a linear map, is a linear map, and you can think of it as expressing one coordinate system in terms of another coordinate system, or a transformation, like from one coordinate system to another. And we can, like the standard things that we do with matrices in computer graphics are rotation, scaling, translation, and projection. And the cool thing about matrices is that they can be multiplied. So instead of having to multiply a vector by, I don't know, 5 matrices or whatever, we can just multiply the 5 matrices once and then multiply all our vectors by just one matrix. Mm. A 4 by 4 matrix product has 64 multiplications and 48 additions, and so it's not really a wonder that special hardware wasn't built for this, because that's a thing that you want to optimize, obviously, and that's of course GPUs, and uh, why why GPUs are so powerful today. Because as I said, linear algebra is just, counting different things at the same time, and that really pops up everywhere. And GPUs are really good at it. So, yep. Okay, now on to the next topic, the render pipeline. So the render pipeline kind of has evolved over the decades or something, I guess. Um, so this version may be a bit simplified, or not so modern, but it roughly matches like yeah, the PS2 hardware era. So like 25 years ago or something like that. Um, well, even longer ago, I guess. So the question is, how do we get from from our 3D geometry, from our mesh, to pixels on our screen? And we do that, like we have two basic parts of that pipeline. One is concerned with the vertices, so like vectors that make pixels. And at some point we convert those into pixels on screen, and then we do things on the pixels. So first step is the transformation and lighting, which is like really heavily linear algebra like based, oriented, whatever. Um, then we have to make sure that the stuff that we're drawing actually is on screen, and we're not drawing over the screen, at least not too much, and that is clipping. So we're cutting off parts of the triangles that we don't want. Then we rasterize it, so we figure out which pixels are actually contained by this triangle. And we shade it, which means we calculate a color for each pixel, and then we write that pixel to the frame buffer so it can be displayed. And now we just go through these different stages briefly. So as an input, we have a mesh, which is a bunch of triangles, really, normally triangles, and could be lines as well, but let's say triangles. And one way to specify them is just as a list. So 3 vertices make a triangle, and this little mesh on the right here might be this list of vertices. Okay, that's pretty simple, but it's not really efficient because we're repeating ourselves a lot. So there is another way to do this, which is called a strip. And a strip is a thing like here on the right, where every vertex makes a new triangle with the 2 vertices that preceded it. So 1, 2, 3 is one triangle, and then 4 makes the next one with 3 and 2. Then 5 makes the next one with 3 and 4. 6 makes the next one, and 7 makes the next one. So it's a lot more efficient to encode geometry in that sort of strip format because of less repetition. So fewer vertices. One thing that might be problematic is that not every mesh can be expressed as just a single strip, but you can stitch multiple strips together, and that thing like in the top right here, that mesh, cannot be expressed as just a single strip. So you have to do some stitching here. So if you want to do it, like you repeat the last vertex of the previous strip and the first vertex of the next strip, and that way you get so-called degenerate triangles, and you can stitch together these strips. But this is like, you can find that stuff everywhere. I'm not going to go talk too much about it. The transformation now is the next step, which is really interesting, because that's exactly what we're good at now that we know all about matrices. And our goal is to send our vertices from model space to clip space. So model space is the space with where all coordinates are relative to the model. So to like the center of the model, more or less, you could say. And clip space is such that the camera is at the origin and looking in the z direction. And we do that by multiplying our points with 3 matrices. The first matrix brings it from model space into a world space. So that means we have defined some kind of global origin, and the first step is to convert the coordinates from model space to that world space. And that's just like a translation and rotation and all sorts of stuff. That's a matrix that belongs to that model that you're drawing currently. Then we have the view matrix, which positions the camera in the world, or actually it does the opposite. It positions everything such that the camera, well, if you position the camera in the world somewhere with the matrix C, then that is really quite similar as putting the camera at the origin, and you move the whole world around it such that it looks the same. And that is what the view matrix is. It's actually the inverse of that camera matrix, which positions the camera. So it's very similar to a model matrix, which moves the model into world space, you might say, and moving the camera into world space is kind of opposite to what we want to do, because we want the camera at the origin, so we move the world like inversely to camera space, or something like that. But they're really quite the same concept, just you do the transformation in the opposite direction, you might say. And then we have the projection matrix, which we've already talked about. So just doing these 3 transformations, of course you can combine them because it's matrices and you can multiply matrices. And then you have just one matrix vector multiplication per vertex if you want to be efficient with it. Okay, next, lighting. So there are certain kinds of lights that you can imagine, and these are just a couple of them. Ambient light is just a constant value, that constant color, so to speak, that you add to every vertex. It's not very interesting. Lambert is also called, like, it's a standard diffuse lighting model, and this one uses the dot product between the normal vector, which is perpendicular to the surface of the geometry, and you typically have to specify the normal vector with the model, and the light vector, or actually the negative light vector. So imagine this one pointing towards the light, and then the dot product will be exactly 1 if they align, which means the brightest intensity, and then it will gradually get darker, and at 90 degrees perpendicular, the dot product will be 0, so there it's black. And if you go beyond, then it's going to be negative, and that's of course also black, but we have to clamp it to 0, because like a negative intensity doesn't make so much sense to us. So this is the standard formula for Lambert, for the Lambert light model. And there's different other kinds of lighting, for instance, 2 kinds of specular lighting, Phong and Blinn. So these gives these that gives these little highlights. And what you do here in Phong lighting is you reflect one vector along another one, so along the normal vector here actually, and So you reflect the light vector along the normal vector, and you take the dot product with that and the vector that's from the eye to the vertex. So that reflected vector dot the eye vector, and you take that and you also raise it to a power, which gives it that these little highlight spots, and you can adjust that parameter to get like tighter or more diffuse spots. And there is a version of that which is slightly more efficient and looks a little bit different. It's called Blinn. And you take the half vector between L and E instead of reflecting it properly. Yeah, but I mean that's just like details. It's not too important to know all the ins and outs of that, I think. But just to give you an idea of what kind of calculations are done traditionally to do lighting. And you combine all of that, and you get such a nice thing here. So yeah, and that was lighting. So now clipping. After transformation, it can happen that the geometry actually does not properly fit onto the screen. So it protrudes like from the edges, or even worse, it's like too far away or too close to the camera, or even behind the camera. And we want to get rid of all that extra junk. So what we have to do is cut those triangles at the essentially at the planes that define our viewing volume. So they have to be in a certain range, the x, y, and z values. And in the worst case, that triangle can turn into a 9-gon, so 9 corners, if it's if it intersects with every single of these 6 planes, then it gets 9 vertices. And from that, we generate new triangles, which is what you see down here. And that's what we draw then. And as I said, it's very important to clip the geometry behind the camera, because a projection always puts everything in front of the camera. So all the stuff that's behind you might become visible due to the projection step. And yeah, sometimes you can get away with simpler means, like just throwing away complete triangles, which is culling. But in general, clipping really is necessary, and yeah, that's a great pain in the ass if you want to do it on the PS2. Okay, now that we have our final triangle, turn them into pixels. So we find out which pixels belong to this triangle, and also what the attributes are at these pixels. So we probably have to interpolate a color or maybe a texture coordinate or something, and every pixel will have that interpolated value. And there is a problem though, especially when it comes to texture coordinates, because if we take the midpoint of an edge, like in proper world space or camera space or something, it might not be the same, like it might not be the midpoint in projected space. So as an example, imagine this thing is like a long wall. It's like, I don't know, many 100 meters long, and the real midpoint of that wall might be perhaps somewhere here. Like if you think this point is very far away and this one is very close to you, then the midpoint might be here somewhere. But in this projected space, the midpoint is obviously more like here. And that's a problem, because to interpolate the values properly, you have to take perspective into account. And it turns out that if you don't do this, you get very ugly effects. So texture mapping, if you do it correctly, you have the right result. If you don't do it correctly, which is called affine texture mapping, you get this weird effect. And to do it correctly, unfortunately, is a bit expensive, because you have to divide the texture coordinate and well, 1 by the depth, by that weight, and then interpolate these values. And to get the real texture coordinate, you have to divide by this interpolated Q again. So that means you have a division for every pixel, and that's not really what you would like, because division is slow and expensive, and having to divide for each pixel is something you would like to avoid if possible. Okay, so we have our interpolated values for every pixel, but now we want to have a color for that pixel. So this is what we would call shading. So we take the interpolated attributes and somehow combine them into a final color. So typically we do texture mapping and modulating that texture by a color and applying fogging. Originally, this was done by fixed function hardware, so just you could apply some settings to it, but with not so much control over it. And this is, of course, what the PS2 does. Today, we have pixel shaders, which are programmable, and there's a lot of stuff you can do with them. You can even do lighting on a per pixel basis. But typically, like originally in the PS2 days, the sort of stuff that you would like to do is modulate the color with the texture and add maybe specular lighting and also do fog of distance sort of stuff. Okay, here's just an example, which I'm sure everyone is familiar with: linear versus nearest texture mapping, or filtering, actually. Okay, and the last step is the output. So we have our final color for the pixel, and we want to write it to the frame buffer so that it becomes visible. And at this stage, we typically have a bunch of tests that the pixel has to pass in order to be written to the frame buffer. So the first is the depth test. So a pixel that is behind something else that has already been drawn is rejected. Which means we have to keep track of how far the pixels are into the screen, so to speak, so that we can decide whether to reject it or not. And that's what we need a Z buffer for. So it stores a depth value for every pixel on screen. Another test is the alpha test, and usually it's used to reject pixels that are too transparent to be visible. And one reason for that is because a pixel that passes the alpha test also writes its depth value. But if its color is really, like, if you could do without that pixel, you don't have to write the depth value, and that may be beneficial to do, actually, because blending is another thing that happens at the output stage. And it's combining this new pixel, like the color of this pixel, with the pixel that was already in the frame buffer. And this is typically used for transparency. And you can see it in the picture here. So you can see in the back, and over that was drawn some kind of leaves from a tree or bush or something, and that's all fine. You can see at the edge, though, that this is where the alpha test is, where pixels stopped passing the alpha test. It got too transparent in this region here, and inside this region, the alpha test was passed. But the problem is that after this thing was drawn, something behind it was drawn, and of course that failed the Z test, the depth test. So even though it would have been visible if you had drawn it in a different order, yeah, you actually have this artifact around the edges, and yeah, wrongly sorted transparent objects are just a big problem because there's really no way to win. Yeah, so it's an artifact that you see a lot. It's just you would have to draw the triangles in the right order, and that's really expensive in a lot of cases, and it can even be impossible. Like if you have intersecting triangles or stuff like that. Okay, so that kind of concludes our trip through the render pipeline, and now for some history. Computer graphics, and especially 3D graphics, has existed for some time already. And we're starting here in the 60s. One of the really early demonstrations of 3D graphics was probably Sketchpad on the TX2. Which I don't have a picture of here, but it was like a CAD program, and it was very influential yeah, in like getting 3D graphics, getting interest in 3D graphics going, and so on. Some other machines were built in that era, like the 60s and 70s. Vector General, for instance, built the hardware that was used. You can see a picture here. Was used to render the trench run animation in the first Star Wars movie. And this other picture I've taken from a brochure on the Evans and Sutherland, I don't know what it was, line drawing system or picture system, one of the two. But at that time, you essentially had like real-time line drawing capabilities. So there were no colors, no lighting, obviously. You can't have light if there is no color, and you don't have textures if you have no colors, and there was no memory for textures anyway. So all these things just didn't exist. You could only draw lines, and that made drawing a lot simpler, of course. However, what you often wanted to have was hidden surface removal. So if you have a line that is behind another surface, you would like to not draw that line, and that's quite hard. There was a lot of people thought a lot about how to do this efficiently, and there's a whole bunch of algorithms for that. Today, we don't need that anymore because we have Z buffers, but back in the day, that was quite a difficult problem. So the hardware at that time roughly could do matrix multiplication, division, clipping, which is easier if you're only drawing lines, by the way, and well, actually also drew lines. So that was the 60s and 70s. Obviously, there was some development. I mean, 2 decades worth of development in one slide is not going to do it justice. Another thing in the early 70s that appeared were early frame buffers. So especially the University of Utah was very, yeah, they just did a lot of research, and a lot of stuff was happening in computer graphics at the University of Utah. And they had a 512 by 512 frame buffer connected to a PDP-11 and later a VAX. And they just did rendering on that thing, and it was really the first time that you could draw, like you could calculate a picture and draw it on a screen in color. Like today, we don't think about it much, but at that time, that was really the first time it was possible. And so obviously they had to think about a lot of stuff, and they came up with all the solutions that we still know about today. So light calculation was something they had to think about, and models appeared in that context. They had to think about shading, like what color do I want on the triangle. So flat shading just gives the same color on every pixel. Gouraud shading interpolates the color across the triangle, and Phong shading even does lighting per pixel. So there's Phong shading and Phong lighting, and it's not the same. Just to be, you might probably should be aware of that. They also did texture mapping, and bump mapping was invented there as well. So here's an example of texture mapping actually. So so that is a picture of the frame buffer. So the top left actually has like what we would consider today the frame buffer, but the same memory was also used for the texture. So they had space for like 1 or 2 textures maybe. So that is the texture they used. And the thing down here was the Z buffer. So they also used the same memory for the Z buffer, and you could actually see it on the screen. So at that time, so like with that hardware, you could also do kind of complex scenes because you just write into the frame buffer, and it just stays visible until you change it. Whereas with the vector graphics, the display also worked differently, and you had to draw fast and so on. But still, calculating just a single frame was pretty expensive. It was really slow. Everything was done in software, so there was no hardware acceleration for this sort of stuff. And we're talking a few minutes per picture, so it's not frames per second, but it's minutes per frame. Yeah, but a lot of stuff was developed at that place in that time. So in the 80s, we start to see some real-time frame buffer graphics. So the Evans and Sutherland CT5 machine was a huge thing and really, really expensive and big. And I think it was the late 70s. And this thing on the right is a screenshot of some flight simulator that they wrote. So quite amazing. And SGI, so Silicon Graphics, came up with developed the geometry engine, which is a vertex. What do you call it? A vertex processor. Um, and they did that using like very large scale integration. So it was actually they built single chips, and it was not some huge racks of like 19-inch racks like the ENS thing, which probably took up a room or whatever. And they did this small, like very large scale integration, but like small scale hardware, small stuff. And so they could actually sell it. And the geometry engine is what started SGI actually. So the Iris workstation was a product they sold. And this thing could do like this sort of hardware could do filled triangles in real time. So previously there were lines in real time or filled triangles but really, really slow, and this was filled triangles in real time. Could do flat or garage shading, but no textures yet. So this down here is a screenshot of a demo running on some SGI Iris machine. So that was like 80s. Okay, and now in the 90s, we have this sort of expensive workstation culture merging with the consumer style PC and console hardware. So in the console space, we have PlayStation 1, of course, and N64, which was mostly developed by SGI as well. And in the PC area, we have Voodoo and Rage and Riva GPUs by like the big names of GPU companies at the time. Voodoo was founded by previous SGI employees actually, and they wanted to bring their stuff to like consumer hardware. Again, N64 was developed jointly by SGI and Nintendo. It was like it's very SGI-like, and the sort of hardware actually does mostly software transform and lighting. So in some sense, maybe a step backwards. So like the geometry engine, for instance, in the 80s already could do transformation in hardware, but yeah, this. Again, this is like consumer style hardware. But the rasterization was accelerated by the hardware, which makes sense. You always want to optimize your tight loops, the things that you run often, and obviously you have a lot more pixels on screen than vertices, so that's the thing you want to optimize for. And just to compare a little bit, the PS1 has no depth buffer. It does affine texture mapping, so it has these wobbly textures as the perspective changes. It has no linear texture filtering, so it's very pixelated, everything that's textured. The N64, in comparison, it does have linear filtering, but a very small texture memory only. It does perspective texture mapping. It does have a Z buffer, and it also has a vector processor, the RSP, to do like. For instance, T and L, but also does the triangle setup stage, which you might think is part of the rasterizer actually. So it's kind of it's not something that's easily programmable though. Okay, and now that leads us to our favorite console, of course, the PlayStation 2. And by various metrics, it's probably the most successful console of all times. It is somewhat similar to the Nintendo 64. So you can definitely see some SGI history in there or inspiration. But one problem was that the N64, whereas the N64 had like a 3D library that like came with a development kit, Sony did not have such a thing. So the developers had to write their own stuff pretty much, or use other third-party libraries, and that made programming it pretty hard. So hardware-wise, we have the PS1 CPU for backwards compatibility and taking over I/O tasks like disk and memory card and controllers. Then the heart of it is the emotion engine, really, which is a MIPS CPU to vector units and some other stuff. The graphics synthesizer is the rasterizer, and for sound we have essentially two PS1 sound processors. So we're going to look into the graphics part of it a little bit more. Okay, so here's a somewhat simplified diagram of the PS2 architecture. So it's missing like the IOP and stuff. Okay, so what do we see here? We have, first of all, we have main memory, 32 megabytes of it, and it's connected to this 128-bit bus to which everything really is connected. So this is the central connecting infrastructure. And on that bus, we also have the main CPU, the EE core, which is a 64 or a 128-bit, depending on how you count, MIPS processor. It's connected very tightly to one of the vector units and uses it as a coprocessor in most cases. And there is another vector unit which is connected to the bus, which mostly is used for transformation, lighting, and clipping, which is especially fun. And the vector unit with its interfaces, so if always stands for interface, as well as the main memory bus are connected to the graphics interface, the GIF or GIF maybe, which is the what you talk to control the GS, the graphics synthesizer. And so with that you send the drawing, the geometry and textures and so on to do the drawing, and it generates the video signal. And there is the DMA controller, which really ties the whole thing together, and it's really important to know what the DMA controller does, and build DMA chains to shuttle around all sorts of stuff. So very interesting or very important is the other three paths to the GIF, actually. So path 3 is kind of the simple one, where you just send directly from main memory to the GIF, usually with a DMA transfer. And this is typically used for textures. And there are two more paths. Path 1 is directly connected to vector unit 1, which is like the geometry part of it, TNL and clipping. So path 1 is where the geometry is sent over. So the geometry enters the VU1 through VIF1, is put into memory, and then after processing it, it's sent to the GIF. And path 2 is sort of like path 3. It's there is no additional processing done. It bypasses VIF1. So you might think, why would you need this? And the reason is synchronization. Path 2 and path 1, because they come in through the VIF, they're synchronized, whereas path 3 is asynchronous to this. So path 2 is most can be used very easily for small data like render state updates and changes. It's not so efficient to use it for maybe pre-computed geometry or textures, but we'll get a little bit into that later. Okay, so just an example for how you can think of these DMA display lists. So display lists are an old concept, really. It's been it's been a thing since the 60s at least. And on the PS2 you have well the PS2 take on it, and it's done by building DMA chains and sending them around. So most importantly, one DMA chain to VIF1 and one to GIF. So everything is in these DMA packets. So the continue packet just contains data. So VIF unpack puts stuff into VU memory. So you might use that to upload like lights or matrix into VU memory, which can be used for a complete object, like maybe a car, and the car never has different lights, so the lights are constant for that same car, or maybe the matrix is constant for the whole car. And then every object may consist of different materials, which like use the same matrix and lights, but have different other properties like color and texture and so on. And you might use a different, so you could perhaps think of this being more like a loop here, different materials. So you unpack your material data, I don't know, color and stuff like that. And then there is a call type of a packet, which refers to, like it points to some kind of destination. And the DMA controller just continues at that point until it reaches a red packet, and then it goes back, and it can do, I think, 2 levels. So in that packet, we might have a ref type which just points at the data rather than having it inline in the list. And VIF direct is the way to send data via path 2. And so here we might have some pixel data, like a texture. It's not efficient, as I said, but it's possible to do it that way. So this would be a way to upload a texture, and then after the texture is uploaded, we call another packet, and this would be the geometry in different, like in a number of batches, because the memory is quite limited. You have to divide the geometry into batches, and then you start the program for each batch, and it will transform and process the geometry data and send a packet to the GS. So that's kind of what a display list looks like. Now for the actual VU microcode, the memory, I mean, you have complete control over your memory layout, but the typical layout is to have 2 input buffers and 2 output buffers, and some region where you keep your like constant data. It's like shader constants and DirectX or uniforms in OpenGL. So what you do is imagine buffer 1 has just gotten some input from the DMA controller, and we started the program. So we will maybe first do some processing on that input buffer, like perhaps decompressing, or I don't know, somehow pre-processing the vertices, and then we might do some lighting on it, and it can all happen in the input buffer. And then we want to transform it to the output buffer. You don't necessarily need an output buffer, but generally it's good to have one. And there are kind of 2 cases you might end up with. So this kind of matches my code, which is based on Renderware's code. You could architect this differently, but this seems like a sort of sensible way to do it. So let's take the easy path, the non-clipping path. So we transform this input to the output essentially by multiplying with the big matrix, the model view projection matrix, and also we do the perspective divide. And once that's done, we just send the packet, and it will be drawn by the graphic synthesizer. And in the clipping path, it's a bit more complex, but let's not get into that here. And notice that we have a double buffering scheme here. So while we're working with input buffer 1, the next input buffer can already be filled in by the DMA controller. So that means we're sort of not trampling, we're not waiting too much for the processor to do its thing, and we're also not like stepping on each other's toes. Like all the different parts work together, and they wait when they have to, but usually you set it up so that they don't have to wait too much. That as much as possible can happen in parallel. Um, that we have a similar parallelism in the output buffer. While the previous batch is being drawn by the graphics synthesizer, we can already fill in the new the new buffer, output buffer. And once this one is finished drawing, we can draw this one, and then the next batch can be transformed, like input buffer 2 can be transformed into output buffer 2. So there's the general scheme of it. It looks, yeah, maybe a bit complicated, maybe not, but if you go into the code, it actually does look a bit complicated. That is an example of my code. So first of all, VU1 executes two instructions always at the same time. We have an upper and a lower instruction, and we have a somewhat longish pipeline. And the first part is just doing some setup, but what's interesting is the loop. So this is where we loop over the vertices, and due to the long pipeline, it's efficient to interleave vertices. So to have in one loop iteration work on multiple vertices at the same time. And this is what I've tried to indicate here with the indentation. So no indentation means the current vertex, the first vertex. One indentation means the next vertex, and two indentations means the next vertex. And so we have three vertices in flight here in that one loop iteration. And this loop is 13 cycles long. Once you're done with that, this xgkick instruction is the important one. This is what actually starts that path 1 transfer, with vi12 being the pointer of the packet. And then we cycle our output buffers, and so we switch buffers. Okay, so that's just to give you an impression for the VU, what the VU code might look like. Okay, so textures are quite difficult because, well, they don't have to be, but to do it efficiently is difficult. There are essentially three ways to upload textures. So one is just do it synchronously over path 2 through the VIF. So in that case, we have like texture for model I, and then we render model I, then we upload texture for the next model, then we draw the next model, and so on. Always texture first, then model, texture first, then model. But that's not really efficient because we're not making use of much. To do that, we need the GIF channel actually. So path 3 transfer. One way to do it is to interrupt the CPU from the VIF1 chain. So whenever I'm ready to accept the next texture, I interrupt and let the CPU send the next texture and restart the VIF transfer as well. Oh, there's a typo here. This is meant to be path 3, not path hash. Anyways, that is the more efficient way of doing it. So yeah, what you can do is you enable path 3 and disable path 3 from path 1. Actually, from this chain. It's not the path itself. And that means when you start working on this model, you can enable quickly, just for a few cycles, you enable path 3, and this will start the upload of the next texture. And then you can sort of handle models and textures at the same time without having any CPU interruption going on, which is not so good for performance. It's still better than this, but yeah, it's called mask path 3, right? So with mask path 3, you can sort of synchronize these two chains. and have texture upload be somewhat more efficient. And of course, it's good to avoid uploads if you can. So caching textures in GS memory is good, but it's only 4 megabytes, so it's not so much. But yeah, this is a challenge of like caching is a challenge. This gating, this path-free gating is another challenge. But that's the fun in programming the PS2, of course. And yeah, actually, that's my last slide. So now I think we'll just to have something that is not slides, we'll go to the quick demonstration. So this is my development machine here, DTL 10,000. And let's see, we have... Okay, so I've been working, I don't know, a few months ago on a new graphics library for the PS2, and some of you have probably seen it. And I call it Ecstasy because, well, emotion, and it kind of relates to emotions. So if you want to be a really emotional, Ecstasy is a fitting name. So let's run that. And yeah, it's just a sphere, but I could also draw a teapot and probably, I don't know, a cube or something. And it actually does clipping. It does textures, not very efficiently, but it can do textures. Has microcode for lighting and without lighting, and optimized for 2D rendering and so on. So that was one thing, and maybe what is that? Some window manager shenanigans. So let's run the other demo, which is a program that renders the first level. It's sort of the hub level of Spyro the Dragon for PS1. So you might wonder, why do you need a PS2 to render a PS1 game? Well, the cool thing is that this is actually drawing the whole world, not just like the immediately like the close areas like the PS1 does, and the rest in like in low quality without textures and so on. And it actually renders everything through the clipping path, which is like the not efficient one. So yeah, that's something that works. I actually don't make use of linear texture mapping for a reason here, because of the tile map way that it works. But you can see the clipping working. Come on. Okay, it's not so easy to get that. Okay, so there you can see the clipping working. But actually what you see is that that the colors are not quite right when it's clipping. It's interesting because the colors are not perspective correct, and the clipping interpolation kind of does not match JS interpolation of the non-clipped polygons. So if you want to be really, really accurate, then you'd have to do the clipping differently. But yeah, I think it's good enough. So yeah, I guess that's all I wanted to show. So it's a nice little demo. Okay, thanks everyone for staying this long. Not everyone stayed so long, but yeah. Okay, that's it.